Hey, today the topic is images produced by curved mirrors. So there's two kinds of curved mirrors that we will be dealing with. One is the concave and one is a convex mirror. And the key difference from a physics point of view is what they do when we shine parallel rays of light towards them. So you notice on this concave mirror that these parallel light beams, these parallel light rays, always reflect through the focal point here. Compare that to what's happening at this convex mirror, where the beams of light that come in parallel reflect such that they look like they originated over at this focal point here. So a real big difference where these beams of light really go through this focal point, and these beams of light don't. For that reason, we say this mirror, the concave mirror, has a real focal point. Convex lens, we use the term virtual for its focal point. So it's got a virtual F. So as we move forward, keep this in mind, the idea of what is a real focal point and what is a virtual focal point. The focal points, whether they're real or virtual, have everything to do with the shape of the mirror. So concave always has a real focal point, convex always has a virtual focal point. So we're going to learn a process called ray diagrams, and what ray diagrams allow us to do is to predict the characteristics of an image that's produced from a different optical device. So we're going to take a look at convex mirror ray diagrams to start with. So first of all, let's highlight a couple things that you need to do before you even get started. Number one, we have our optical device here, our mirror right here. It's going to be a concave mirror, so this is the shiny side. And the real focal point for this concave mirror is right here, so I've labeled that with that green dot. And then I've made another dot here that refers to something called the center of curvature. From a geometry point of view, the center of curvature is always twice the focal point. So if the focal point is, say, 5 centimeters, then the center curvature is another 5 centimeters for a total of 10 centimeters. And these 2 points give us some reference points to draw a ray diagram. The other thing that we need to have here is this line that runs horizontal on our page here has the focal point and center curvature on it. It's called the principal axis, so say the PA. So you'll hear me refer to the principal axis. It's just that line that we use for a reference. It's a horizontal line. Now, I put an arrow here, and this arrow represents the object. So in any situation where we're getting an image from a mirror, it's because we put an object somewhere in front of the mirror. And the easiest shape to use that still gives us an idea of what happens to the image is to use an arrow, because it's got an obvious top and an obvious bottom to it. All right, so let's get started with the ray diagrams. The biggest tool that you'll use is a ruler. And that's because light travels in a straight line, so when you draw your rays of light, you always want to draw nice straight lines. And the first ray that we can draw is a ray that goes from the tip of the arrow, runs parallel to the principal axis, so it travels in this direction, and then that ray of light, as we already saw, always reflects parallel to the principal through the focal point. So I'll draw a reflected ray that goes through the focal point, and in theory never really ends. It just keeps going on and on. As you do more ray diagrams, you'll see sometimes you have to make that reflected ray longer. Sometimes it's not necessary to draw it too long, but I'll start there. So that's my first ray. Let's number that ray number 1. It's the one that I've drawn in purple. The second ray, let's choose a different color here. Let's try green. The second ray of light is one that you'll see a common theme to the start of this. They always start at the tip of the arrow, tip of the object, the top of the object in this case. This one is kind of the reverse of the first one. It is a beam of light that starts at the tip of the object, the arrow, and then goes through the focal point. So let me just get that lined up. So we go from the tip of the arrow, goes through the focal point this time, hits the mirror. So I'll just give a direction here so we know when we're done which way everything went. And that beam of light reflects, well, it's symmetrical with the first ray. It reflects parallel to the principal axis. So ends up looking something like that. Move my ruler out of the way. So there you go. The first two rays. The first one went parallel to the principal axis. The second one went through the focal point. The first one went parallel to the principal axis and reflects through the focal point. The other one kind of does it in a different order, through the focal point, then parallel to the principal axis. Let's number that number 2. Now, in theory, we now have all the information we need in order to find out what the image would look like and approximately where it would be located. But I'm going to show you, because we're learning this for the first time, if necessary, there's another ray that you can draw. And that ray is the one that, if you went from the tip of the object and lined up your ruler with the center of curvature, let's get another color here. Any beam of light that does that starts at the tip of the arrow, travels through the center of curvature, hits this mirror. Now, I'm glad this kind of happened. You'll notice that I'm actually missing the mirror here. Do not worry too much about that. Just draw the ray as if it hit the mirror, as if the mirror was extended forever and ever. So don't worry if it doesn't physically hit the mirror on your page. Just imagine that it does and continue on. So, put that back. So any beam of light that travels from the object and hits the mirror as it travels through the center of curvature, hits the mirror, is going to reflect straight back on itself. So actually, I shouldn't have even moved my ruler. This beam of light will actually hit always at exactly 90 degrees to the surface, or 0 degrees to the normal line, if you want to think of it that way. And it will hit this mirror and then bounce straight back. So it'll actually bounce back exactly in the same direction it came. So it hits and bounces back. All right, so we'll move my ruler out of the way. Now, here's the thing. What we're looking for is, where do these beams of light hit? But more importantly, the question we ask is, where do the reflected beams of light hit? So you'll notice that this is a reflected beam right here. Okay, the purple reflected beam we're looking at. So that's it right there. The green reflected beam is right here. And the blue one is on top of it. So there's the incident ray, but it bounces straight on. So there's a reflected ray right here. And you'll notice that there's an intersection point right here where all 3 of these reflected rays intersect. And that's what we're looking for. This will tell us where the tip of the image will be. If this is the tip of the object that we started with, this is the tip of the image. The rest, we just fill in, knowing that if we did every point along this object, we would find every point along this image would just take us back to the principal axis. So we can now draw a straight line from where this tip of the image is produced. Draw a straight line. If I can do that. Draw a straight line from here to here that represents our image, I. If this was our object, this is our image. All right. So the 3 reflected rays all meet at one point. That tells us where the tip of our image will be. All right, there. Cleaned it up a little bit, cheated a little bit, grabbed my tool for lines, and there you go. So this is, in the end, the image that is produced. Now, when we're done, we also like to write down the characteristics of our image. So, image characteristics. There are three things we are looking for. One is the size of the image. So I'll just highlight this, although you can just, when you're done, write the size down. So you really have three choices. Is this image bigger than the original object? Is it smaller, or is it the same size? So you can see the benefits of just drawing a nice simple line. We can see clearly, and if you wanted to, you could pull out a ruler, but you can see pretty clearly that the image is shorter than the object. So we will say the image is smaller. The next thing that we'll look at is the orientation. All right, so the orientation really just says, have we flipped this thing upside down, or is it still right side up? Because you can get both those possible outcomes. And again, because we did a nice arrow here, let's get my ruler out of the way. Because we did this arrow here, it makes it really obvious that this thing, in the end, became inverted. The other word we would use, if it was right side up, the choices are inverted or erect. But clearly in this case, it's inverted. And then finally, we have the last characteristic, which is the type of image. Now this one is at first not totally clear until you've done enough ray diagrams and you've seen both types. So we have a choice here between a real image and a virtual image. Now you have a sense of what we mean when we talk about real and virtual when it came to focal points. Same kind of rule here. If the beams of light, if the rays of light really intersect at one point, and that's where we draw our image, then we call it a real image. If they don't really intersect, if they only virtually intersect, we call them a virtual image. So this one is nice and neat. It's a real image, and so we'll just categorize it as such. But keep in mind, you'll see other ray diagrams in which the image is not real, it is virtual. So that's our first look at ray diagrams with a concave mirror to start with. I'll put up some more lessons with different mirrors and different lenses eventually, but it's probably best just to look at one at a time. And so this is your first look at a concave mirror.